Welcome students, Module 3 Covalent Bond. The instructor of this video is Mrs. P. Arunajyoti, Assistant Professor in Chemistry, St. Joseph's College for Women. Students need to learn the applications of valence bond theory. We know that valence bond theory is the greatest overlap criterion can explain how the covalent bonds formed in a variety of compounds. It hints at the establishment of the strongest conceivable bonds. Among its most significant uses, it is the one which is very important. For instance, the variation in the overlapping of orbitals between H2 and F2 molecules can account for the variation in the length and strength of their chemical connections. Valence bond hypothesis explains that the overlapping of the hydrogen atoms 1s atomic orbital and fluorine atoms 2p atomic orbital. The fact is that hydrogen and fluorine shared electrons, which results a covalent link in an HF molecule. It is a very significant theory. This theory, which describes the formation of covalent bonds, applies to a wide range of substances. Limitations of valence bond theory. Valence bond theory does not explain the odd electron species. The examples for the odd electron species are NO2 and ClO2. Both are carrying single unpaired electrons. The existence of unpaired electrons in this species cannot be explained by valence bond theory. We know that according to valence bond theory, half-filled atomic orbital overlapping can take place. After overlapping, some of the electrons are left over as unpaired electrons. The existence of unpaired electrons in such a species cannot be explained by valence bond theory. It was the first limitation. Coming to the next limitation, valence bond theory is unable to explain the paramagnetic nature of the oxygen. What do you mean by paramagnetism? We have heard three terms, right? Diamagnetism, paramagnetism, ferromagnetism. If you keep any substance or a species in the magnetic field, some of the substances are strongly attracted towards the magnetic field, but some of the substances are strongly repels the magnetic field. If any substance strongly attracted towards the magnetic field, then it is a ferromagnetic substance. If any substance slightly attracted towards the magnetic field, then we can say that it is a paramagnetic substance. If any substance repel from the external magnetic field, it comes under the category of diamagnetism, right? According to valence bond theory, O2 is a diamagnetic substance, but experimentally shows O2 exhibits paramagnetism. That paramagnetic nature of the oxygen does not explain by the valence bond theory. It was very precious limitation of the valence bond theory. The next drawback is it fails to explain the fractional bond orders. NO shows the fractional bond order that is 2.5. The next example, CO plus can show that bond order is 3.5. These most of the molecules got fractional bond orders, right, which cannot be explained on the basis of a valence bond theory. Coming to the next limitation, we know that sigma bonds are very stronger than the pi bonds. But in N2 molecule, pi bond shows very stronger than the sigma bonds. It cannot be explained on the basis of valence bond theory. Coming to the next limitation, C2. The number of bonds operated between a carbon and carbon in C2 molecule is 2. Among the two bonds, one must be a sigma bond, another must be a pi bond. The formation of the pi bond in C2 molecule cannot be explained by the valence bond theory. The next one is maximum bond order. According to the valence bond theory, the maximum bond order was 3. But some of the molecules containing more than 3 which cannot be explained by on the basis of the valence bond theory. For example, CO plus shows the bond order is 3.5. The next one is fails to explain the color of the halogens. Here we have different halogens like fluorine, chlorine, bromine, iodine. No, all this exhibiting some color. The color cannot be explained by the valence bond theory. All these are considered as limitations of valence bond theory. Valence bond theory leads to hybridization. First, allows me to explain what is hybridization. It is a word means mixture. If you mix salt with a water, you may get a mixture. When you mix sugar with the water molecules, you can also get a mixture, right? Similarly, consider two atomic orbitals, S and P atomic orbitals are combined or intermixed to form just like the mixture of water with a salt or water with a sugar. How can you define the hybridization concept? It is a phenomenon of intermixing of atomic orbitals having the similar energy and proper symmetry when they get hybridized to form hybrid orbital. This concept is known as a hybridization. We must learn that why we need to learn hybridization concept. Well, the hybridization of atomic orbitals teaches us two important concepts. It shows us the first concept is molecular geometry or shape of the molecule. Secondly, it shows us the bonding of atomic orbitals. You will learn more about the molecular geometry and bonding of atomic orbitals in this lecture. Secondly, why atomic orbitals are hybridized or why hybridization takes place. Well, there are different theories which explains the concept of hybridization. But valence bond theory fails to explain how the atomic orbitals gets hybridized. According to valence bond theory, suppose if you take a methane molecule, the outermost electronic configuration of the carbon atom is has 2 electrons in 2s atomic orbital, 2 electrons in a 2p atomic orbital. It is a ground state electronic configuration. When it is excited, uh, in excited state electronic configuration, you must write the 1 electron in 2s atomic orbital and 3 electrons in 2p atomic orbital. Here, you should jump the electron from lower orbital to the higher orbital. The next higher orbital is 2p. So, there is only 1 electron in 2s level, 3 electrons in 2p level in a excited state electronic configuration of carbon atom. Okay. So all these 4 electrons provided by the carbon atom gets intermixed with the 4 hydrogen atoms containing single electrons. As a result of this, we can observe 4 types of overlapping. Those are SS, it is a SS overlapping, SP overlapping, SP overlapping, SP overlapping. 4 types of overlapping. Okay, the extent of SS overlapping is lesser than that of extent of SP overlapping. Due to this reason, suppose if it happens, how can you get the equal number of bonds formed between the carbon and hydrogen atoms? And one more doubt arises, how can we get the shape of the methane molecule? At this particular point, the valence bond theory has not succeeded. It was explained by the hybridization concept. Students, what did you understand in the previous slide? That is, there is a direct overlapping takes place between atomic orbitals of the carbon atom and atomic orbitals of the 4 hydrogen atoms. As a result of that, you may notice that 4 kinds of overlappings such as SS overlapping, SP overlapping, SP overlapping, and one more SP overlapping. The extent of overlapping between 2s atomic orbital is lesser than that of extent of overlapping in sp. Due to this, the variation occurs in the strength of the sigma bonds. Thus, how can we get equal bond angles, and how can you get the shape of the methane molecule? It is an impossible molecule formation, and it could not be understandable. It is 100% wrong. Okay. According to the hybridization concept, we will get the shape of the molecule. Methane molecule shape is tetrahedral shape. Here, the carbon atomic number is 6. Electronic configuration is 1s to 2s to 2p2. If you look at the ground state electronic configuration of carbon atom has 2 electrons at 2 levels, 2 electrons at 2p level. In excited state electronic configuration, only 1 electron present in the 2s level, 3 electrons present in the 2p orbital. All these 4 unpaired electrons from 2s orbital and 2p orbital gets hybridized to form 1 plus 3, 1s 3p atomic orbital gets hybridized to form 3 plus 1 4 hybrid orbitals. These 4 hybrid orbitals of the carbon atom overlaps with the 1s atomic orbitals of the 4 hydrogen atoms, which makes the angle as 120 degrees. Okay, the obtaining sigma bonds from the methane molecule is 4 sigma bonds. We will get the equal bond angles between the carbon atoms and hydrogen atoms, and the shape also exhibited by the methane molecule is tetrahedral shape. From this concept, we can define the hybridization in which one atomic orbital overlaps with the another atomic orbital. When the atomic orbital overlapped with each other, they could have the proper energy and proper symmetry. Then only they are involving in the hybridization to and it have the ability to make a hybrid orbitals. This concept is known as hybridization. It could be possible, and it could be understandable. 100% right concept. I would like to explain about the hybridization technique. This hybridization concept was introduced by Pauling. The idea of combining two atomic orbitals to create a new class of hybridized orbitals is known as hybridization in chemistry. Usually, this intermixing of the atomic orbitals leads to the development of hybrid orbitals with completely distinct energies, forms, etc. The majority of hybridization occurs between atomic orbitals of the same energy level. But as long as they have the same amount of energy, half-filled and fully filled orbitals can likewise participate in this process. Conversely, we may argue that the idea of the hybridization is a continuation of the theory of valence bonds, and that it clarifies the creation of bonds as well as their lengths and energies. Fully filled and half-filled orbitals can also take part in this process. We know that it is an extension of the valence bond theory. This hybridization concept helps us to understand the formation of bonds, bond energies, bond angles, bond length, and magnetic properties of certain molecules. Students, you must learn the conditions required for hybridization technique and also the features of the hybridization process. The first condition of hybridization was the enthalpies of the orbitals involved in hybridization must be only slightly different. Whatever the atomic orbitals involved in hybridization must possess either identical enthalpies or slightly different enthalpies. The second condition applied for the hybridization was the orbitals that are being hybridized are usually from the atom's valence. The outer electronic configuration containing atomic orbitals can only actively participating in hybridization, but inner shells containing atomic orbitals doesn't involving in a hybridization process. That was the second condition. The third condition is it can happen between orbitals that are totally either they can totally filled or half filled or unoccupied atomic orbitals. All these are the conditions applied for the hybridization technique. Let us see the features of the hybridization. The next first point is the energy of the orbitals participating in hybridization should be close to the same. Whatever the atomic orbitals participating in hybridization, both atomic orbitals should possess the energy must be equal. The unequal energies of the atomic orbitals doesn't participating in the hybridization technique. The next point is hybridization occurs when the orbitals of one and the same atom interact. Here, the interaction or the intermixing of the similar type of atomic orbitals of the same atom participating in a hybridization, but the uh, atomic orbitals of the different atoms cannot be involved in a hybridization technique. The next one is the total number of hybrid orbitals generated is the same as the total number of hybridized orbitals. Uh, how many number of atomic orbitals involved in a hybridization technique? It must be equals to the number of generated or obtaining hybrid orbitals. That is the third feature of the hybridization. Coming to the next point, in terms of shape and energy, the hybrid orbitals are all the same. You know that a hybrid orbital that participate in a bond formation must have at least one electron. The participating orbital should have at least one electron. Then only we can see the hybridization process. The hybrid orbitals tend to stay at the maximum distance apart due to electrical repulsions between them. These hybrid orbitals should always maintain some distance. Why? Because of there is some operation of electrical repulsions between them. The next point was sigma bonds are formed by the overlap of atomic orbitals. How will you get the sigma bonds? By end-to-end overlapping of any two atomic orbitals, we will get the sigma bond formation. By sidewise or lateral overlapping of atomic orbitals, we can easily form the pi bond formation. All these are the required features of the hybridization. Let's go to the next one. We can watch the different types of hybridizations. Hybridization is a concept that explains the formation of different types of bonds and shapes of molecules by mixing atomic orbitals of different energies and shapes. There are different types of hybridization based on the number and type of orbitals involved in the mixing process. Here are some examples of hybridization with the diagrams. Based on the types of orbitals involved in the mixing, the hybridization can be classified as sp, sp2, sp3, sp3d, sp3d2 and sp3d3. You just don't bother about the sp3d3. We have to learn the remaining hybridizations like sp, sp2, sp3, sp3d, sp3d2. Let us now discuss the various types of hybridization along with their examples. All the images in this video have been taken from Google Chrome. Thank you.